Hey there, physics students. In this video, we're going to review a free response question in preparation for the AP Physics 1 exam. The description of the problem is as follows. Part of the track of an amusement park roller coaster is shaped as shown above. A safety bar is oriented lengthwise on the top of each car. In one roller coaster car, a small 0.1 kilogram ball is suspended from this bar by a short length of light inextensible string. Light means mass is negligible. Inextensible means it does not stretch. The string does not stretch. The mass of the ball is 0.1 kilograms. And let's see what they ask us to do. So they say initially the car is at rest at point A. So first of all, point A is a place along the track. You can see it's labeled B, C, D, and E. So different parts of the track have different labels. And the first section is asking about part A, or at point A, where the car is at rest. Now, at rest has some important characteristics. At rest means no motion. It also means no change in motion. And the key to that is that the acceleration is zero, meaning there's no change in motion, there's no change in speed, so it's going to stay at rest. Okay, on the diagram to the right or below here, draw and label all the forces acting on the 0.1 kilogram ball. Well, we know that gravity acts on the ball, and that causes a weight force, which we might label mg. And we know that if that was the only force acting on the ball, then it would be falling towards the center of the earth, but it's not because there's a tension force that is provided by the string. Now, when you draw a free body diagram, you always want to make sure your force vectors begin on the object and point away from the object to show their direction. In this case, we know that we're at rest, we're at equilibrium because A equals 0. That means these upward forces are equal and opposite. Upward and downward forces are equal and opposite. You could mark them somehow to show that they're equal, or just draw them as closely to the same as you can. So that would be acceptable for your free body diagram. That's always a good first step for any force problem, is to draw a free body diagram. The next thing it says to do is to calculate the tension in the string. When they say calculate, they mean get a number. We want a numerical final answer. So first step in a force problem, draw a free body diagram. Second step, make a second law statement. Second law, sum of the forces equals mass times acceleration. So F equals ma. But in this case, the acceleration is 0, which means the force is 0. Okay, the sum of the forces is 0. So the acceleration is 0, the sum of the forces is 0. Okay, so let's see if we can calculate the tension in the string. So we know that the tension acts up, the mg acts down. Let's go ahead and choose positive as the upward direction, which makes sense. That means the net force, or the sum of the forces, is T up, mg down, so plus T minus mg equals ma, but in this case, ma equals 0. Do a little algebra, you'll see that T equals mg, which equals 0.1 kilograms, the mass of our ball, times 10 meters per second squared. Why not 9.8? Because this is an AP test, it's timed, and it's perfectly acceptable to use 10 to make your math easier. It even says that in the directions. 0.1 times 10 is 1 Newton. So that is our tension in the string, okay, is 1 Newton. Awesome. Okay, next step. Now we've got some interesting explanation here, some description of what's going on. I'll give you a little diagram so you guys can remember what it looks like. And they say that the car is then accelerated horizontally, goes up a 30-degree incline, goes down a 30-degree incline, and then goes through a vertical circular loop, the radius of which is 25 meters. For each of the 4 situations described in the problem, do all 3 of the following. Do all 3 of the following. We'll see what that means in a minute. In each situation, assume the ball has stopped swinging back and forth. So this ball is stable in its position in the car in each of these situations. All 3 of the following for each of the problems subsequent are 1, 2, and 3. So those are the 3 things. The 3 things are to determine the horizontal component of the tension, TH, the vertical component of the tension, TV, and to show that in the diagram the approximate direction of the string with respect to the vertical. So in other words, where is the ball? What is the ball doing in each one of these cases? Okay, in the first one, we looked at position A, where the ball was at rest. We drew a free body diagram. Now we're going to go to position B, okay, which is on the horizontal part of the track. The car is moving horizontally with an acceleration of 5 meters per second. So we have it, the car is no longer at rest. It is now accelerating at 5 meters per second. That means it's moving to the right in this case with an acceleration of 5 meters per second squared. Now, if it's accelerating at 5 meters per second squared to the right, that means the ball is going to be hanging down to the bottom towards the back of the cart, okay, or in the opposite direction of the acceleration. Okay, now it doesn't ask us to do this, but I'm going to go ahead and draw a free body diagram because that's always a good first step of your force problems. So there's our ball. We know that the mg force acts down still, just like it did before, but now, as we can see, the tension is acting up at an angle, okay? And that's because the car is accelerating. Okay, now that's it for our free body diagram. However, in order to solve the problem for the components, the horizontal and vertical components, we need to break this tension down into its horizontal and vertical components. Now I'm going to change colors only because I'm drawing components now, and these don't typically belong on a free body diagram, but because we're looking for them, I'm going to go ahead and put them in. So TV is the vertical component, TH is the horizontal component of the tension. Okay. Well, what we need to do is we need to solve for these two components separately. So the first one I'll do is I'll go ahead and solve for the vertical, just because I can see there's two forces in the vertical. Again, free body diagram first, second law statement next. Sum of all forces in the vertical equals ma in the vertical. Now we have no acceleration in the vertical. It's not moving up or down. It's not changing its position or its speed up and down. So that means the sum of the forces in the vertical is 0. What are the forces in the vertical? Again, we have tension in the vertical up, that component, minus mg down, and that equals 0. When we solve for TV, you'll see we get TV equals mg, and that equals, again, 0.1 kilograms times 10 meters per second squared, and that means TV equals 1 Newton. Okay? We'll go ahead and plug that in here. 1 Newton. I guess I can put an N there. Oh, it already has an N. That's okay. Okay, in terms of the horizontal component, we can do the same thing. We can say, okay, the sum of the forces in the horizontal equals M times A in the horizontal. We know we can see that there's only one force in the horizontal, that's the TH, and that's going to equal M times A in the horizontal. And we know everything. We can plug and chug. We can now say equals 0.1 kilograms times 5 meters per second squared, and 0.1 times 5 is TH is going to equal 0.5 newtons. Okay, so we're going to plug in 0.5 newtons. Okay, I guess I didn't need the newtons, but that's okay. Okay, so that's the second part. That's position B. Okay, position C looks like we're going up the incline. We're moving up the incline, but this time it says not an acceleration. It says we're moving at a constant speed of 30 meters per second. Now, constant speed, again, is just like being at rest. The acceleration is 0, because if the speed isn't changing, then the acceleration is 0. Okay. We need, again, the horizontal and vertical components of the tension. And where's the tension? Where's the string going to be? Well, the string's going to be going straight down because, of course, there is no acceleration. So gravity is going to be the only force pulling it down. There's no change in the motion of the ball. So let's draw a free body diagram. Mg, T up. And so now we can see that these two forces are equal and opposite. So we can simply say the sum of the forces equals ma, but we have no in the vertical, and we have no acceleration in the vertical, no acceleration in the horizontal either, but this equals 0. And so now we can simply say TV minus mg equals 0. TV equals mg, which we know again is 1 Newton. Okay, we'll go ahead and plug that in. And in the horizontal, well, because it's constant speed, that means it's not changing its speed horizontally. That means this is going to be 0 newtons in the horizontal because there is no acceleration. Okay, position C looks like we're going down the ramp, and certainly we are. I'm sorry, position D, pardon me. That was position C. Position D is going down the ramp, but it's not going down the ramp at a constant speed. It's accelerating at 5 meters per second. So it has a net acceleration down the ramp. Okay. Now, if it's accelerating down the ramp, okay, let's make sure we know that that's at 30 degrees to the incline. That's going down the ramp. The ball is going to be swung back away from vertical, because if it was going at a constant speed, just like at the last one going up the hill, it would be vertical. But because it's accelerating now, we know that it's going to swing back from vertical back to here. Okay? Let's go ahead and draw a free body diagram. There's our ball. mg down, tension up at an angle, and we know that this is going to accelerate downward. Now, this is the tricky part of this problem. The best way to solve this is to think about in terms of the acceleration. If there's an acceleration in this position or in this direction, that means there's a net force in that direction. And the net force comes from the resultant of the mg force and the tension force. And that net force is going to be down at 30 degrees. Okay? And that net force, I'm just going to say that's the sum of the forces on this ball. And that's going to equal ma. Okay, that's what that green line equals. Now, where does that come from? Well, that force comes from the tension and the weight force. But that force has a components that are horizontal and vertical. So we have a horizontal component of that net force. And interestingly, that's going to be resulting from the tension. Okay, so that's going to be the M, we'll call this MAH, because that's the MA force, but the horizontal component. And it's also going to have an MAV in red here. Call that MAV. Now that force is downward and it's going in a negative direction. And that's because it's going down a ramp that has an angle theta equal to 30 degrees. And this vertical component of the force comes from the weight force, and whatever component of the tension is vertical too. Okay, let's go ahead and draw in the tension force. That's the vertical component. We'll call this TV. And we know, oh, and TH is just MAH. So that means we could also label this TH, because that is where that force comes from. So TH equals MAH. Okay, so at this point, we're ready to start thinking about what these forces actually are. Well, let's go ahead and take the horizontal section first. So let's start. So we got our free body diagram. Again, only the dark blue vectors would be in your free body diagram. The rest of these are all components or resultant forces. So in the horizontal dimension, sum of the forces in the horizontal dimension equals M times A in the horizontal. Now we already know the only force that acts is TH, the tension force, and that's what we're looking for, the horizontal component of the tension force. And then it's M times A in the horizontal dimension. Well, the horizontal component of MA, remember MA is what gets it down the ramp. The horizontal component is the adjacent side of that triangle, so that means that's going to be the A times cosine of theta. Let's go ahead and plug and chug. TH equals 0.1 kilograms. What's our A? Well, it's 5 meters per second squared. 5 meters per second squared times cosine of 30 degrees. Now, if you don't remember your cosines and sines, check your equation sheet. 0.866 is cosine of 30. So we got 0.1 times 5. That's 1/2 of 0.866. So that's TH is going to equal 0.43 newtons. So we'll go ahead and put that in here, 0.43 newtons. Our next point is to calculate the vertical. Now we got to think about this carefully in order to make sure this works. So first of all, notice that we've got vectors in two directions, pardon me. We've got up vectors, the vertical up, we've got vertical down, and we've got another vertical down, okay? If we continue with our convention that upward is positive, we can start making our second law statement. Okay, so our second law statement, I'm going to start over here. So we're going to look at the vertical. So the sum of the forces in the vertical dimension equals the mass times the acceleration in the vertical dimension. Okay, and we know that that mass times acceleration in the vertical direction is the part that is downward and getting it down in the vertical direction. Okay, well, what are the forces in the vertical? Well, we've got TV up, we've got mg down, and that's all going to equal MAV, but MAV is in the negative direction, so we're going to say this is equal to negative MAV. And we say that because, of course, MAV is in the negative direction. But AV is the opposite side of the triangle, so that means it's going to be MA sine theta. Okay, now we do a little algebra, and we can check your algebra. It's going to be TV equals M times G minus A sine theta. Let's go ahead and plug and chug. Check your algebra if you need to. 0.1 kilograms times the quantity 10 meters per second squared minus 5 meters per second squared times sine 30 degrees. And if you remember, sine of 30 degrees is 1/2. So let's see what we got. We got 5 times 1/2 is 2.5. 10 minus 2.5 is 7.5 times 0.1. TV equals 0.75 newtons. So 0.75 newtons. Now that should make sense, because if the tension were vertical, it would be holding up the entire 1 Newton of force. But because it's pulling back and because this whole system is accelerating downward, the tension doesn't have to pull up nearly as hard because it's accelerating downward. So the tension in this cable or in the string in the vertical dimension is 0.75. Okay? Okay, last part of this problem. Oh, now we're into blast from the past, circular motion. So as this cart swings around that circle, it swings around in the loop. Okay, so we're down to point E. We're coming back. The cart's up at the top of the loop, and it's pointing this direction. And you can see they show that by its speed is moving in this direction. It's moving tangent to the circle. It says the car is at point E moving upside down with an instantaneous speed of 25 meters per second and no tangential acceleration. No tangential acceleration. So we can treat this as a constant speed, because there's not going to change that tangential speed because there's no tangential acceleration. Now, if you remember, as this moves in a circle, there has to be a force inward on the circle to keep it moving. And we'll remind you guys that the force inward is called the centripetal force, and that equals mv squared over r. Okay, so that's just a reminder of centripetal force. Now, as this ball swings around in this circle, it's going to be just like a ball on a string, and so the ball is actually going to be upward in the car, like so, as this car moves around the circle, just like you were twirling a ball around on the string. Okay, so let's take a look at our free body diagram, and we know, let's see, we've got mg down, that's always true, and we've got tension down. I don't know which one's bigger yet, but I'm just going to draw those two different forces so we can see them. And so we've got these two forces. Well, we know that this is moving in a circle, so it must be accelerating, and that's because there's a net force or centripetal force on it. So we can make a second law statement again, and we can say that the sum of the forces equals MA. Okay. Now, in this case, this acceleration is a centripetal acceleration, so we can say that this equals mv squared over r, and that's always the case for something moving in circular motion. So, what are our forces? Well, we have two forces labeled here, mg and t. Now, the convention for a centripetal force, or forces causing centripetal motion, is that towards the center of the circle, so anything towards the center of the circle, in this case it would be towards the center of the loop, and we're on the top of the loop, so it would be pointing towards the center of the loop, that would be positive. So both of these forces are technically going to be positive. So we can just say mg plus t equals mv squared over r, and we know that this tension is vertical. I'm going to label that there, and we can then solve for the vertical tension. You check my algebra, but it says I'm going to say that it's going to be TV equals m times v squared over r, the centripetal acceleration, minus g. Okay. Let's go ahead and plug and chug in here. We get TV equals 0.1 kilograms times, I'm just going to leave it as 25 meters per second squared over 25 meters minus 10 meters per second squared. Well, 25 squared over 25 is just 25. Minus 10 is 15. 0.1 times 15 is 1.5, so that TV equals 1.5 newtons. So we can plug that in here as 1.5 newtons. Now, TH is going to be 0. Now, why is it going to be 0? Because it says there is no tangential acceleration. That means in the horizontal dimension, there's no force, there's no acceleration forward, there's no acceleration back, there's no acceleration, therefore there's no net force. Okay, that sums it up. This is a pretty straightforward question. There are a few little quirks in it that you have to kind of think a little carefully about. Typically, you'd get about 25 minutes to finish this problem. We talked through it and hit all the points that I think were important. If you're curious, this particular question appeared on the AP Physics B exam in 1995. Okay, thanks for watching, and we'll see you next time.